So in 4.4, we're going to be solving the non-homogeneous case so that this right-hand side here is non-zero. Just as a refresher, remember that when you're trying to solve this in general, you actually have to do this in two parts. You've got to find what's called the homogeneous solution and a particular solution. So even when the right-hand side is not zero, you still first solve when it is zero, or solve as if it were zero. That's where your general solution part comes in. That's where your C1 and C2 enter. But then you've got to try to find a single solution with no C's in it whatsoever, just one single solution that if I were to plug it in the left-hand side, I get the right-hand side. Okay? So the claim here is that if YH, this guy, solves this one, and YP solves this one, then together this one up here, this one down here, but together they also solve this one. Solves, and solves. So YH solves 2, YP solves 1. My claim is, with a virtual number of arrows here, unlimited supply of arrows I can throw at you, that the whole thing solves it. Now, all I got to do is plug that in, right? So let's consider if y is equal to YH plus YP, two separate functions, just by using the properties of derivatives being linear. The derivative of y is then YH prime plus YP prime, whatever they are. And y double prime would be YH double prime plus YP double prime. Now I take this, and I'm going to stick them into equation 1. So what I'm left with is an A y double prime, which is YH prime prime, plus YP prime prime, plus B YH prime, plus YP prime, plus C YH plus YP. Now regroup. And you have A y sub h double prime plus B y sub h prime plus C y sub h together plus A y sub p double prime plus B y sub p prime plus C y sub p. Now this, since YH solves 2, we know that AY sub H double prime plus BY sub H prime plus CY, right? Since when I know if it solves 2, then that whole thing has to equal 0. And down here, what is this equal to if YP solves equation 1? Again, what does this whole thing now equal if YP is a solution to equation 1? G of t. Since the YH part goes to 0, this piece over here goes to 0, so you end up with G of t, which proves that this new thing, which is just a combination of YH and YP, solves G of t, or solves 1, equation 1, namely gives the right-hand side as G of t. Okay? And why is this YH plus YP better than just YP? I've already told you YP solves 1, so why do I need YH at all? Because I need a general solution. I need a 2-parameter family of solutions so that I can solve initial value problems. I need C's in there so that I can find specific solutions that go through specific points. And the YP does not have C's in them, but the YH does. The YH is where my general parameters come from. So that's why we call that combination, YH plus YP, the general solution, because it depends on two constants, as in the last section. So how we find particular solutions, how we find the YP, that's what 4.3 and 4.4 are all about. Or sorry, 4.4 and 4.5 are all about. We're going to cover two. There are actually more methods out there than just these two. We're going to stick with these two. It'll be general enough for us. We're going to do the method of undetermined coefficients, or as I like to call it, guessing. And we'll do the variation of parameters. Which actually technically is better guessing. But it's a different kind of guessing. With guessing on number one, I'm actually trying to figure out just what that function looks like. On variation of parameters, I recognize that it could possibly be, well, we'll get there. I don't know how to explain it without actually just explaining it. So that's what 0.5, that's what 4.6 is all about. All right, the educated guess method. So here's the y double prime plus 3y prime plus 2y. If it were equal to 0, you know how to solve it. So you know the first step of a second order linear with constant coefficients problem already. But now let's try to find y sub p. Let's just focus on that step of the process. We need to find a function whose value that we get after plugging it in on the left-hand side leaves behind a 3t. We need a function where y ends up as a linear function after having its 0th, first, and second derivatives combined, right? I'm going to have a y here, I'm going to have a y prime, and I'm going to have a y double prime. So here's what my best guess would be, is if the right-hand side is a linear equation, why not try a linear function as a guess? Right? The right-hand side looks like a constant times t. Let's try at, where a is now an undetermined coefficient. But at is my yp. This is my guess. I'm not telling you that's what it looks like. I'm just saying, is there maybe an a that if I plug in there would make that satisfy this? So now check if such an a exists so that y1 solves the DE. In other words, just plug it in and see if we can't solve for A. All right, so y1 double prime plus 3y1 prime plus 2y1. What is, we'll just come over here and do it. What's y1 prime?
A.
And y1 double prime?
0.
So I have 0 plus 3 times A plus 2 times AT. So now what I'm going to do is I'm going to set that equal to this. So this says 3a plus 2at equals t. So this is one of those cases where this is not really a conditional equality so much as we want this to be identically equal. That is, we want the left-hand side to equal the right-hand side for all t. So we need this linear equation on the left to equal this linear equation. The problem is, the way that you set two polynomials equal to each other and solve is you have to set their coefficients equal to each other, right? We've done that kind of thing before. When we set their coefficients equal so they're identically the same, we end up with, well, what's the constant term on the left-hand side? 3a. What's the constant term on the right-hand side? There is none. So 3a has to equal 0. Now the linear term, right, by the way, this is like 1t plus 0 is what I'm thinking of it as, right? As a polynomial, every degree power is there. So this constant has to be set equal to that 0 right there. Now this one's going to have to be equal to that 1. So I'm going to have 2a equals 1. Do you see the problem?
Yes.
You can't solve both of those simultaneously. So a equals 0 and a equals 1/2, not possible. Okay? You can't solve simultaneously. Right? There's no 1a I can plug in here that makes the left-hand side equal to the right-hand side. We're disappointed.
Hey, what? How did you get the 3 away from t?
Oh, I don't know. 2/3.
Oh, okay.
Thank you. Thank you. I don't know where that 1 came from. That was when I wrote this over here, I got crazy. Thank you. My bad. But still the problem remains the same.
Right.
Even though I confused you along the way. So let me restate again what I said. You can't find an a that makes both of these solve both of these at the same time. But here's kind of the revelation. How many equations did I end up with whenever I eventually set these equal to each other? 2, right? So what if my educated guess had 2 parameters in it instead of just 1? What would be a better guess than AT?
Let's see.
Or plus something, right? Let's have both of the terms of the linear equation there. Can I find a general linear equation that satisfies that? Okay, better guess. So let's try it. Okay, again, now what's y2 prime? It's actually still a,
Oh, yeah, sorry.
and y2 double prime is still 0. So now we plug it in, y2 double prime plus 3y2 prime plus 2y2. I'm just plugging it in to the differential equation in the problem, and I'll have 0 plus 3 times a plus 2 times at plus b. And set that equal to the same thing again, 3t. So now let's group t's together. So in this case, I now have a 2at, and I have, actually I just put this together. I'm going to put the constant together. So 3a plus 2b has to be equal to 3t. I don't guess I need these lines in here to make any point here. I just distributed the 2, and then I put these 2 terms together as one. Now what do you have as your equations? 2a has to be 3, and 3a plus 2b has to equal 0. Two equations, now two unknowns. We are going to be able to solve this. So a is 3/2, which means 3 times 3/2 plus 2b equals 0. So that's 9/2. Move to the other side. 2b is negative 9/2, and b is negative 9/4. So what's your solution then?
Y equals 3/2 t plus negative 9/4 or minus 9/4.
I'm going to call that my y sub p. And just let's confirm to make sure we understand what we've accomplished here. If I do, check this, right? Yp prime is 3/2, yp double prime is 0. If I plug that all into yp double prime plus 3 yp prime plus 2yp, I get 0 plus 3 times 3/2 plus 2 times 3/2 t minus 9/4. That gives me 9/4 plus 3t minus 9/4, which gives me 3t. Right? Just confirming that this process found a linear equation that when I plug it in the left-hand side, I get the 3t out on the right-hand side. Okay? So here's what we've learned. If you have linear on the right-hand side, your best bet is linear on the left-hand side. Guess a linear form. In fact, that's going to work in general for polynomials. If you have a quadratic, guess a quadratic. If you have a cubic on the right, guess a cubic. A general cubic with all the parameters in there, like ax cubed plus bx squared plus cx plus d. Plug it in, set the two sides equal to each other, and solve the resulting system. Okay? So strategy number 1, if the right-hand side looks like that, nth degree polynomial, guess an nth degree polynomial. Okay, next example. The right-hand side is constant times e to the 3t. What do you suppose would be a good guess, you think, for what y sub p would be? Again, keep in mind, what you're going to want to happen is that on the left-hand side, when you plug it in, you take a derivative, you take a second derivative. A combination of those results in a constant times e to the 3t. So what would you guess?
A t cubed plus b t squared plus c t, I guess.
Plus d?
Plus d.
Okay. Well, that's not t cubed. That's what I would do if I had a t cubed on the left-hand side.
Why'd you write it?
Because he said it. I thought I'd write it down. Now think about this, Nikolai. Why this is going to pose a problem is whenever I take the first derivative and second derivative of this, and plug it on the left-hand side. On the right-hand side, I have e to the 3t.
Okay.
First and second derivatives of this don't produce an e to the 3t for me to handle, right? For me to match up with.
Yeah.
So
A e to the bt.
a e to the bt. Okay. Now when I take the derivative of this, I will get an ab e to the bt and then an ab squared e to the bt, right? So on the left-hand side, I have e to the bt's. On the left-hand side, I have what? This 10e to the 3t. So the only e to a power that's showing up on one side is e to the 3t, right? So on the left-hand side, yes, left-hand side, I really only need e to the 3t's. I don't need any other things in front of the t. I just need e to the 3t. So I would suggest that we don't need a general b up there. We just need 3t.
Do you want to add a constant so that's solvable?
Well, let's see. I mean, on the again on the left-hand side, I'm just taking first and second derivatives in the original functions. On the right-hand side, there's no constant term, and there's actually no constant term that's going to just show up over here, right? Because when I take yp prime, what do I get?
Good. 3a e to the 3t.
And then if I do yp double prime,
9a e to the 3t.
9a e to the 3t. Notice when I add up a combination of these three things, there's no constant term like there was up here. So I understand your concern, but up here I ended up with just a 3a by itself stranded that I had to set equal to 0. I won't end up with a stranded constant down here. So I don't think I need this plus c. Plug it in, right? So you get 9a e to the 3t plus 3 times 3a e to the 3t plus 2 times a e to the 3t equals, set it equal to, 10 e to the 3t.
So then you just get rid of all that e to the 3t's. 20 equals, or 20a equals 10. A equals 1 half.
Yep. So 20a e to the 3t equals 10 e to the 3t. Which means 20a has to equal 10. So a has to be 1 half. I've now solved that uniquely. So I claim y sub p equals 1 half e to the 3t is a particular solution.
These guesses are only like particular solutions. They're never.
Right, so to get the homogeneous is when we go back to the characteristic polynomial.
Okay.
To get the particular solution, we're looking at the form on the right and guessing what would possibly work with some unknown coefficients in there. So we have two cases now. We have the t to the n case and we have the e to the some power t case.
Why can't we guess when it's just equal to 0?
It's not homogeneous.
Well, because when it's equal to 0, we aren't looking for a single solution. We're looking for a general solution. We need the c's in there, right? And there are no clues as to what that... Well, I should say there are no clues. That's exactly what we did. If you go back and look at when we first derived it, I guessed that the solution was e to the mt. And then we found the m that made that work. So I guess essentially that's how we created our method with the characteristic polynomials, was by a good guess. All right, now there's another problem here that's kind of lying hidden that needs to be brought to your attention. And I don't have room for you to do it, so here. So go over to the back page of the previous one and just think about if it was y double prime plus 3y prime plus 2y, and I'm going to take riskiest risk of all in the differential equations and make up a problem off the top of my head to discover what my problem is here. Imagine that that's equal to 10, not e to the 3t, e to the minus 2t. So following the same technique, what would be your guess?
A e to the actually negative is gonna go in front.
And just to kind of give you a little bit of a heads up, the problem is not that it's negative. The problem has to do with this being part of the homogeneous solution. Watch what happens. What is yp prime? Well, negative 2a e to the minus 2t, and yp double prime is 4a e to the minus 2t. Okay? So, now, 4a e to the minus 2t plus 3 times a minus 2a e to the minus 2t plus a e to the minus 2t. Have to set that equal to 10 e to the minus 2t. And I left out a 2 right there, sorry. All right, this 2. Do you see the problem?
0.
0 equals 10 e to the minus 2t. There's no a. Uh-oh. Okay, so why did that happen? Well, remember what the characteristic polynomial would look like in this case. M squared plus 3m plus 2, right? Which factors to m plus 1, m plus 2. So m could be negative 1 and negative 2. Right? Which would mean that the y sub h is c1 e to the minus t plus c2 e to the minus 2t. This right here is part of the homogeneous solution. It is a solution to the homogeneous equation. When that happens, that means if I were to plug this in and any combination of it into this, I got to get 0 because it is a solution to the homogeneous one. It will give me 0 on the right-hand side. Okay? So, how do I guess better? Answer. Throw in a T. Do you remember how we just threw in a T whenever we had repeated roots?
Yes.
So if I throw in a T now, I know that this thing is not a solution to the homogeneous because negative 2 is not a repeated root. Now what's yp prime? Gets a little messier. Got to use the product rule. First times the derivative of the second.
Negative 2at is negative 2t.
Plus second times the derivative of the first, a e to the minus 2t. Which I would write as negative 2at plus a times e to the minus 2t.
Okay.
Because it's, well, it's product rule again. That's why. Yp double prime. First times the derivative of the second is this whole thing. Actually, I don't care if I write it this way.
Well,
You didn't like that
I was-
anyways.
yeah.
You were skeptical. Doesn't matter. Just take the derivative again. It's just a habit I have. All right, negative, no,
Negative
positive
4.
4a
Oh, yeah.
t e to the negative 2t times, second time the derivative of the first minus 2a e to the minus 2t. And then the derivative of this is minus 2a e to the minus 2t. So I get a 4 at e to the minus 2t minus 4a e to the minus 2t. Now plug in. So now you have yp double prime, so 4at e to the minus 2t minus 4a e to the minus 2t plus 3 times minus 2a t e to the minus 2t plus a e to the minus 2t plus 2 times a t e to the minus 2t. So the 4at minus 6at plus 2at all cancel each other out. And what I'm left with is minus 4a e to the minus 2t plus 3a e to the minus 2t, which is just minus a e to the minus 2t. Now it's not gone. We've got the a we need, and we set that equal to this thing that I had up here, 10 e to the minus 2t. So it's all about how good your guess is. And you got to pay attention to things like whether or not it's already an existing root of the homogeneous version. So a now, negative a has to be 10, so a is negative 10. So your y sub p for this would be negative 10t e to the minus 2t. Okay. Okay. Now, think about it. In general, when I'm asking you to solve one of these things, the whole process is going to start by you finding the y sub h, and then you finding y sub p. So it's not extra work to notice that e to the minus 2t is already a problem. Whenever you find the homogeneous solution, if the particular guess you have contains one of your homogeneous solutions, you know you're going to need to insert an extra t. That's what this little suggestion box here on the next part of your notes tells you. If the right-hand side is ce to the kt, then use ae to the kt, unless k is a root of the characteristic polynomial, and you'll use, I don't know why I have an x in there, I need to fix that. That's a t right there. A t to the m e to the k t. Where m is the multiplicity of the root. So if it's a single root, if that e to the kt, or sorry, if k is the single root of your characteristic polynomial, then you use t to the first. That's what we just saw in the example I did. If it's a double root, you would have to use a t squared there, because then e to the kt is part of your fundamental set, and t e to the kt is part of your fundamental set. All right, now let's throw in some sines and cosines, shall we? All right, so my first guess might be this. A sine of t, right? Kind of like I did with the e to the kt. I just used the thing that was over there. Okay, but here's the problem. What's yp?
A cosine of t. Oh, and then negative a sine.
Okay, and yp double prime is negative a sine t. The problem is here. Why is that a problem? The problem is there because when I plug that in here, I get cosines on the left when I don't have any cosines on the right. So we fail.
B1 divided by cosine. A sine over sine t, or a tangent t.
We need an IA sine t. I'm going to do a B cosine t. I'm going to have both of them in there. Okay? All right, I've had too much coffee this morning and have gone through a whole water bottle, so I'm going to let you try that while I take a moment. Plug that in, see if you can't solve for A and B. Stupid video I recorded when I paused my recording when I had to step out. Excuse myself. Now somebody's missed all the good stuff. I'm going to scroll back up and just let them take a gander at this masterpiece up here. Whoever's going to watch our video later. Any of you, or, you know, it's on the web, so I'm sure there are millions of people around the world who want to see this.
I was actually impressed with the view counts on your channel.
I'm surprised how they kind of creep up over time, and then, like
40,000.
certain ones, for some reason, like a professor here or there will discover that that's the one they want to share with their students, and then kind of word gets out. And so I've got like the derivative of inverse functions has a surprisingly large number of views on it from Cal 1 last time I taught it. Countable and uncountable sets has a surprisingly large number.
Where were the views from?
Mostly, probably about 70 or 80% America, but there's still quite a few around the world. All right, enough looking at that. Let's come back to this guy. All right, for derivative first times a second plus AT squared plus BT plus C e to the t. Okay, so on the left-hand side, I have double prime, so I'm going to take all of this. 2a. I could simplify it, but I'm not going to. I'm just going to write it all the way in there. 2a to the t plus b e to the t plus 2a t plus b e to the t plus at squared plus bt plus c e to the t plus 4 times the original, which is a t squared plus bt plus c e to the t. And that has to be equal to 5t squared e to the t. So what I'm going to do is I'm going to group these in the categories of t squared e to the t's, t e to the t's, and constant e to the t's. So here are the t squared e to the t's. Here are the t e to the t's. And then here are the constant e to the t's. And don't forget your coefficients out front. Okay, so I've got an at squared and a 4at squared, which gives me 5at squared e to the t, plus, now the blues, I've got a 2a plus 2a, which is 4a. I've got a 4a plus 2b. And then factor out t e to the t. That seems right. Oh, nope, 4b, not 2, 2b. That's should be a 5 here. Right, don't forget this distribution. So I had 4 of those, and one of those has 5. I have 4 a's, and then another, I've got a b and a 4b, so that's 5b here. And then the constant ones, I've got a 2a, 1, 2b, and a c plus 4c, which is 5c. So 2a plus 2b plus 4c e to the t equals 5t squared e to the t.
Can't you?
So this has to match this, since, has to match this, since they're both t squared e to the t terms. But the other ones have to be 0 for this to work. So I have a 5a equals 5. I have a 4a plus 5b equals 0. And a 2a plus 2b plus 4c equals 0. And that's a nice forward substitution problem because a is then 1. And now I have 4 plus 5b equals 0. So b is negative 4/5. And then I have a 2 plus 2 times negative 4/5 plus 4c equals 0. The rest is algebra. So 2 minus 8/5, that's 10/5 minus 8/5, which is 2/5, plus 4c equals 0. So that's a minus 2/5 on the right, so divide by 4, that's a minus 2 over 20, or minus 1/10. That doesn't seem right at all. Let me try that again. Oh, and this is a 5 again. I messed that up again, didn't I? This here and this here should be 5c. Fortunately, that only messes this up right here. All right, so divide that across. That actually c is a negative 2/25. That matches what I got before. So, assuming all that's correct, my particular solution then is at squared, so 1t squared minus bt, or plus bt, is minus 4/5 t, minus 2 over 25 e to the t. Sorry about my midstream miscalculation from the 5C, but we got it corrected. All right, any questions about that? So you got to get a good initial guess, and then from there you got to keep track of a lot of parameters. Okay, so the next page gives you a little bit of a general strategy on how to handle combinations of these types of functions on the right-hand side. So, case 1 says that your initial guess does not contain a function that is in the homogeneous equation. So assume for a moment that that thing that happened up on my previous example that caused me to go off to the right, this thing over here, doesn't happen. That's case 2. Let's say that our guess does not contain any of our homogeneous solutions. This gives you a broad kind of set of examples of where your good choices might be. The first 4 of these are pretty obvious. Those are the polynomials. If you got a polynomial on the right-hand side, use a polynomial as your particular guess of matching degree. So if it's a constant, use a constant. If it's a linear, use a linear guess. If it's quadratic, use a general quadratic guess. Cubic, use a general cubic guess. And so on up. The next 2 are like our next example. When you add a sine or a cosine on the right-hand side, you use the same sign. That is, if it's sine of 4x, you use a sine of 4x and a cosine of 4x. If it was a cosine on the right, you use the same guess. If you have a simple exponential, e to the 5x, use a constant times e to the 5x. If you have a polynomial times an exponential, then use that polynomial of that degree times an exponential, that same exponential. If you have an exponential times a sine, we didn't do one of those, but use that exponential times a sine and that exponential also times a cosine. Notice I'm using both of them there. Even though I only had sine, you got to use sine and cosine both each time. If you have a polynomial times a sine, well, that's where it gets a little messier. You're going to use a polynomial of that degree times a sine, but you also need a polynomial of that degree times a cosine. And what if you have a polynomial times an exponential times a sine, or a polynomial times an exponential times a cosine? You use the same polynomial degree times the exponential times the sine, plus the same polynomial degree times the exponential times the cosine. Starting to get the idea?
Yes.
Okay. So there's not a nice short way to write that. You've just got to get through practice and look at some other examples to try to find those. By the way, if the right-hand side is maybe a combination, like it's a polynomial of degree 3 plus an exponential, then that goes back to your offline homework assignment that I gave you for number 7b. If the right-hand side is the sum of two things, then if you can find the solution to one part of it and the solution to the other part of it, then the solution is the sum of the two solutions. So, for example, if you had maybe a cubic plus an exponential, you would need this plus this. Now that covers what seems like a fairly broad range of functions, but actually it's a fairly narrow in general. They're the functions we use most, so they come up a lot in this level of class, but you'll notice one thing that's missing immediately are maybe other trig functions, maybe logarithms, maybe other types of relationships like dividing polynomials, rational equations. You're missing a lot of things from this, even though it's got a lot of things included. And that's where the next technique is going to come into play.
Can you stick a differential equation into the left-hand side and then have like differential inside of a differential?
A differential equation on the left-hand side? I mean, the left-hand side?
Sorry.
On the right?
The g of x. Yeah. For the g of x.
Well, I mean, the differential equation is in terms of y. Right? So it's already, I mean, y primes, y double primes, or whatever. I'm assuming that we take all of those that may be on the right, move them into the left-hand side, and this technique only works when the result of that process results in a linear with constant coefficients on the left-hand side. Okay? So if I had a y triple prime cubed on the right-hand side, this chapter doesn't apply to that, because it only applies to linear. And for now, at least through 4.6, it's only going to apply to constant coefficients on the left-hand side. Like I don't have any x's in front of here, or in front of here, or in front of here. So while you're seeing a complicated technique, that's one of the kind of things that lets the wind out of your sails in differential equations, is that you realize all this muscle that I just developed applies to a very specific differential equation. Okay? It's still muscle, but you know, it's like the muscle that allows you to use this finger instead of the whole body exercise.
Pretty important muscle.
It is an important muscle. Without it, life changes dramatically. Let's not solve these. Let's guess our particular solution form. Before I do that, case 2. What happens if one of your guesses, that is your particular solution, contains a function that's already a solution to the homogeneous equation?
It's T cube, right? Whatever.
You put in an extra
T.
t or x. I'm going to, again, need to fix that. That's t there. And you put a high enough power on that t that eliminates any duplication of that function in your guess. Okay, so first thing you really need to know is what's the homogeneous solution to this? Are you advanced enough now in your skills with the homogeneous that you can actually write it down without any work? I bet you could. I'm asking you to do 4.3, the entire section in your head. What is y sub h? Remember, you find your characteristic polynomial. M squared plus 2m minus 3. Factor that. You get an m plus 3 and an m minus 1. So you're negative 3 and positive 1. C1 e to the negative 3t plus C2 e to the t. Done. You just did 4.3 in your head.
Oops.
Now, the point is if e to 3t shows up by itself in one of these down here, or e to the positive t does, then I'm going to have to insert that extra t to the whatever power. In this case, just a single power. All right, so what would you guess your y sub p is if the right-hand side was 7 cosine of 3t?
A cosine of 3t plus B sine of 3t.
Right? Which number did you look at? I mean, other than just knowing that that's what we did before. That would be like number
6.
5 and 6. In particular, 6. Just as cosine. Now, on this one, you see that you've got a polynomial times an exponential times a sine. What degree is your polynomial?
First degree.
First degree, so it's linear. So you need a linear times an exponential times a sine plus a linear times an exponential times a cosine. So it looks like a t plus b e to the t sine of t plus, you just keep going up on your parameters, c t plus d e to the t cosine of t. Now, e to the t sine of t, e to the t cosine t is not one of these solutions. Neither is at e to the t sine of t or ct e to the cosine of t. So I don't need any extra t's in those cases.
You don't need any extra t's even though you have an e to the t?
Right, because it's an e to the t sine of t together.
Okay.
It's only when it's by itself. So like if I had somewhere in here, if I were to multiply this all the way out, if I had a constant times e to the t, and that was the entirety of the term, then I would need to insert an extra t in each of those places.
So you really just insert t where like A, B, C, D word?
Well, I can just put it up front like here.
Okay.
And I'd put it on both of them. All right, now this is a polynomial times a cosine. What degree? Second, so I need
AT squared plus
AT squared plus BT plus
C
C
cosine
cosine of pi t
plus DT squared plus ET plus F sine pi t.
exactly. 6 unknown parameters, which would result in 6 equations to be solved.
Why?
D is easy, isn't it?
Yes.
But it's part of this, so what do I need to insert?
T.
A t. Because e to the minus 3t is a homogeneous solution.
So, AT.
Okay,
Oh, there's more.
next one.
AT, AT.
Okay, so y, this is a polynomial times an exponential.
Oh, wouldn't it be AT squared? Oh.
So let's write it down first, or what our guess would be, and then let's look for parts of the homogeneous solution. I would normally do AT plus B times e to the t, right?
Homogeneous is E to T.
But a constant times e to the t is part of the homogeneous solution. So I can't have that as part of this. By part, I mean one of the terms, added part of it. So I stick an extra t in there, or use it as at squared plus bt e to the t. Since bt is be to the t, sorry, is part of homogeneous solution. And F is exactly the same. I don't know why I have it in there again, but it's the same idea. Your y sub p here would be an at squared plus bt plus c e to the t, but because that right there is in the homogeneous, then I need an extra t. Once I put that t in there, you notice I have at cubed plus bt squared plus ct e to the t. None of these terms appear in the homogeneous solution. So imagine, again, keep in mind that you could end up in your homogeneous solution with things like t e to the t. That happens when you have repeated roots. So if you have a repeated root in your homogeneous solution, you may need a t squared instead of just a t multiplied in. All right, I do not have enough time to solve this in its entirety. So I'm going to do that in a video here in a few minutes. In fact, I'm going to stick around as soon as everybody leaves. I'm going to record it right here, right now, and then post it. But this homework is still due on Tuesday, so that you should be able to do that. So if you want to stick around and watch me work this problem, by all means do so. If you need to get out of here, then get out of here, and then watch the video over the weekend, and make sure you know how to do this. This is the entire problem where you find the homogeneous, the particular, then plug in the initial conditions to find the final solution to the initial value problem. It's the full applied problem. So this would be like if I had a spring, I've got one mass, I've got no friction, and I've got the stiffness is 1, but I also have an external driving force on my spring modeled by this equation. My initial conditions are given here. I want to solve and find what's the motion of that mass over time.